last time we saw when you're trying to decide if something's a strong acid, weak acid, strong base, weak base. The strong acids are on the things we should know list. There were the 8. So that was the hydrochloric, hydrobromic, hydroiodic, periodic acid, chloric acid, prochloric acid, nitric acid, sulfuric acid. Just saying it again because the more times you hear it, the more likely you are to be able to remember them. Strong bases had to be soluble, so quite often that means they had an alkali metal. Those are always soluble. And they contained oxide, hydroxide, or amide. For everything else, if it's the conjugate of something strong, then it doesn't do anything. If it's the conjugate of something weak, then if it's a conjugate of a weak acid, it is a weak base. If it's conjugate of a weak base, it is a weak acid. So let's go ahead and let's see why. Let's see why, if it's a conjugate of a strong acid, why it does nothing. So the definition of a strong acid is that strong acids dissociate 100%. So if I put hydrochloric acid in water, I don't do that equilibrium arrow because it's not going to go partway. It's going to go 100%. 100% of that acid is going to give up its H+. So when you have hydrochloric acid, we can say you don't actually have HCl. You really have H+ floating around and chloride. So there's just that lone chloride. In the Le Chatelier lab, we saw when we added hydrochloric acid to the saturated sodium chloride solution, we precipitated sodium chloride because we were adding chloride ion. So HCl is really just chloride ion and H+ ion. That H+ ion attaches to the water to make hydronium, so one extra H. And since this was neutral and I'm adding an H+, it's that. So strong acids dissociate 100%, which means the conjugate of this strong acid is chloride, because it differs by one H+. Chloride is just HCl with the H, without the H+ on it. Chloride, if I put it in water, it's going to react 0%. Chloride, this reaction doesn't go this way, so chloride doesn't even react with the hydronium. So chloride, when I put it in the water, nothing happens. Doesn't dissociate. So the conjugate of a strong acid, I like to say, is a nothing base, because we're so used to saying the conjugate of an acid is a base, but this is a base that doesn't do anything. It's a spectator ion, so it is a nothing base. Okay, so the conjugate of a weak acid, why is the conjugate of a weak acid a weak base? Well, if we have a weak acid, such as hydrofluoric acid, this nasty thing, it's going to dissociate to some degree. So we can say some will go this way, some won't. So that fluoride will be taken off because we're taking the H off. That H will go onto the water to make hydronium. Okay, so what that means is some fluoride would actually go back the other way. So if I took fluoride and I put it in water, some of the fluoride will react with the water as a base. So this weak acid has a conjugate weak base. And the stronger this weak acid is, the more likely it is to react this way, and then the less likely the fluoride is to come back. And of course that'll be fluoride putting it in water, but we can see a tendency. The better the weak acid is at reacting, the worse the conjugate weak base is at reacting. So let's identify some. So right away, I know, again, strong acids are the 8 acids I need to know. Strong bases are soluble and have oxide, amide, or hydroxide. And then for the other things, I look for conjugates. So this was a strong acid, it's on my list. It starts with an H, so it's an acid. It's not on my list, so this must be a weak acid. This guy, it's soluble because it contains an alkali metal, and there's the hydroxide we talked about. So strong bases are soluble and contain hydroxide, oxide, or amide. So this guy is going to be a strong base. This one, lithium oxide, I've got, again, alkali metal, so it's soluble, and oxide, which is one of the 3 things that strong bases contain. So that is also a strong base. Then I have this, ammonium, which we haven't talked about, and we've got chloride. We kind of talked about that being the conjugate of a weak acid, so if we remembered from previously, we would know that that is nothing. I'm going to look into this one more on the next page. This is an ionic salt. I want to see how ammonium behaves in water, how chloride behaves in water, and then I'll know. So here we have phosphoric acid. I know it's an acid because it starts with H. It's not on my list of the 8 strong acids, so this is a weak acid. This is acetate ion, and this is the H attached to the acetate ion. I know it's an acid because it has this extra H, and I know it's not on my list of 8 strongs, so this is going to be a weak acid. So acetic acid, we can also call it ethanoic acid for the 2 carbons. And then we have this one. So we have an alkali metal and hydroxide. So we know it's soluble. It contains one of those 3 things we talked about, oxide, hydroxide, or amide. So this has to be a strong base. And then this was the 1 weak base. Remember, we said the weak bases wouldn't be soluble containing those, or we would memorize ammonia. I try so hard. Okay, so then finally we have this salt. I'm going to look at this one some more too. I'm going to divide it into the 2 parts. I don't recognize this on my 8 list. There's no H at the beginning. Really, I'm going to have to divide this into the positive part, the negative part. I'll see how this behaves, I'll see how this behaves, and then I'll figure out if this is an acidic salt or a basic salt. Was there anything else I wanted to look at? I don't think so. So, did I miss one? Oh, I made one up. Okay, this one we're going to look at too. So, I divide these into 2 parts, so I can say I have ammonium ion. It's positive. It's most likely going to be acidic, because if I put this in water, water's made of hydroxide and H+. This would probably be more likely to give an H+ to the hydroxide, and that is what's going to happen. So this guy, it's in equilibrium. We have ammonia being produced, and we have water. So I recognize this as one of those bases we said we had to know. This is a weak base. This differs by 1 H+, so these are conjugates. If this is weak base, its conjugate is a weak acid. So that means that the ammonium part acts like a weak acid. What about the chloride? So the chloride, when I put it in water, if it were to react, this negative part would be attracted to an H+ to make HCl, and it'd be leaving behind hydroxide. I know HCl is a strong acid, and actually a strong acid with a strong base even. I know this would go 100%, so if this is strong, this is nothing. Strong acid conjugate, nothing base. So that means this part is acidic, this part does nothing. Overall, this ionic salt, when I put it in water, acts as a weak acid. Then we have lithium fluoride. So again, I'm going to divide these 2. Lithium, alkali metals really don't do much. They're always soluble. So this lithium plus, if it were to do something, this positive would be attracted to the hydroxide in water. So, and it would leave behind an H+. So what would happen here, I would actually make LiOH. We're leaving behind H+. Crazy. So with this, I've got this strong base. So I know it's going to react 100%, plus I have a lone H+. So I'd probably actually need 2 waters here and take off one of the H+. Regardless, I'm saying I'm making this strong base. The conjugate of that strong base is going to be nothing. Okay, conjugates of strong things don't do anything. So this guy's neutral. Fluoride, we know if I put the fluoride in water, it's negative. So this negative part of the fluoride would be attracted to the positive part of the water, the H+. So if something happens, it's going to make HF, and it's going to leave behind some hydroxide. Okay, so here I have a weak acid. I recognize this as, it's got to be an acid, starts with an H. It's not on my list of 8, so it's got to be a weak acid. That means it reacts to some degree. That means this fluoride would also react to some degree. Weak acid has a conjugate, weak base. So in LiF, the lithium is neutral, the fluoride is a weak base. Overall, if I put lithium fluoride in water, it acts like a weak base. And finally, we've got this copper 2 nitrate. For the copper, I can say copper 2+, if anything in water, it would be attracted to the negative part, right? Oops, I'm jumping ahead. So that positive copper, if anything, it's going to be attracted to hydroxide. So I know that I would have copper hydroxide, or it could make a complex ion and have If this is a 2 plus, up to 4 hydroxides. We'll see that later. Okay, and we're leaving behind some H pluses, right? Because we're taking the hydroxide off. All right, this is not a strong base. It's a strong base if it dissolves. But copper hydroxide, if we look at our solubility rules, hydroxides tend to be insoluble unless they're with alkali metals. This is not an alkali metal, so this thing isn't fully soluble. So that means copper, when it goes in water, it does collect some hydroxides. So this would happen to some degree. So since this isn't a strong base, but it is basic, I can say that this is going to be weakly acidic. Okay, and then nitrate, it's negative, so if it's attracted to anything in water, it's that positive H plus. So it would take an H plus off, making HNO3, that's nitric acid, and I recognize that as being off my list of 8 strong acids. So if this is a strong acid, it reacts all the way, that means nitrate doesn't react. So if this reacts all the way, it's a strong acid. This is its conjugate, nothing. So the copper was weakly acidic. The nitrate is the conjugate of a strong acid, it does nothing. So overall, if I put copper to nitrate in water, it'll be slightly acidic. And to look at the strength, we can look at the strength of conjugates. We saw that strong acids had a nothing conjugate base and weak acids had a weak conjugate base. The stronger the acid, the weaker its conjugate. Let's look at a few. So here's H3PO4, so I have phosphoric acid. Its conjugate is if I take off one of those hydrogens, and it becomes dihydrogen phosphate. So this is a weak acid. So this is its conjugate, it differs by 1 H plus. So this would be a weak base right here. In this equation, and the reaction the way it's set up right now, it's the conjugate weak base. In the next reaction, I take that dihydrogen phosphate, I'm putting it in with water, and here I'm showing that it can give off a second hydrogen, because I went from H2PO4 to HPO4. So here, on this side, it was gaining a hydrogen to go this direction, so it's acting like a weak base. It's the conjugate weak base of this acid. Here, it's donating a hydrogen. Things that donate an H plus are acids, so it's not on my list of 8. It's a weak acid here. Donates an H. This is the conjugate, differs by an H plus. If this is the acid, this is the base. They're both weak. Weak base. And here is ammonia. We memorize that as one of our weak bases. If I put this weak base in water, it makes this conjugate. This guy differs by 1 H plus. If this was basic, it's acidic. They're both going to be weak. So weakly acidic. Just so we could see a few. And we already saw HCl's conjugate was chloride. Strong acids have a nothing conjugate.